Hello. So last time we were together when I was talking about coffee, we talked about caffeine structure. In caffeine structure, we have a what we call a six-member ring and a five-member ring. And we talk about that it's very similar to the hormones, which I cannot pronounce its name. Adenosine. And we talk about the effect of caffeine replacing adenosine so we don't get tired. So today we're going to continue talk about the caffeine a little bit more as part two. So we're going to talk a little bit about the what happens when you drink coffee, basically, or tea in your liver. So liver is a beautiful chemical company or chemical factory, I should say, and it does things to the caffeine molecule, makes new ones, and each one of those new ones have a different effect on inside our body. Then caffeine is really poison for many species, insect especially, and when a tree or bush generate caffeine, it actually using it as a tool and a weapon to kill the insect. And I'll show you a slide or two of what happens when the spider take caffeine in. And it's also very poison for cats and dogs. So if you have cats and dogs at home, make sure that uh, you don't give them any caffeine, including chocolate. Chocolate has a lot of caffeine in it. Then we're going to go talk about a little bit about textbook. Textbook has a number of examples that the author is using caffeine for us to practice. So let's look at I'll go bring the spider picture up. So as you can see, make this adjust a little bit. When we have the regular spider here, and then makes a web and etc. It's just normal. But if the spider get exposed to a very small amount of caffeine, a big amount will kill it. But a small amount of caffeine, you can see he or she actually doesn't know how to make the web. And I call it like they lose their mind. Again, so repeat, especially for cats and dogs, the caffeine is very poison. And for us also, if you take a big chunk of it. Okay, so I guess I jump back and forth. Anyway, liver now. So if you go to look at the liver, and as I said, liver is beautiful factor, chemical factor. So what liver does, it chops the methyl groups. Remember, we have three methyl groups uh, as part of the caffeine structure. So if you remove one methyl group on the top, we call what new molecule we're going to use it and make it. It's called paraxylene. Now, if you take the other methyl group, we call it theobromine. I forgot why we call it theobromine. So this methyl group is gone here. Over here, this methyl group is gone. And then if you remove the methyl group from the five-member ring, we call it a theophylline. Now, each of these also are active inside our body. The first one, it help for the fat to become fuel. So the athletes can run faster and we can do a little bit more. The second one, which we make, the liver makes about 12%, helps with the oxygen. We carry the oxygen in blood, and because of that, the nutrient also goes a little bit faster inside our system. And the last, the 4%, actually increases the heart rate. And that's what people have heart problem. They usually the doctor tell them not to do or take a lot of caffeine. Or if they do coffee, like I am, make sure that you don't take a lot of it. Just make sure that makes 1 cup a day or something that I do. Now, how we make coffee? There are many different ways we make coffee. The simple uh, coffee machine that we have here is basically the writing is not clear. So we have basically we put the coffee ground here, and then you put water. So they're very similar. So the water basically is cold here. There's a little valve here that prevents the hot water coming back out. You don't want that, right? You want the cold water to go in and not come back. So the cold water goes in. There's a little heater here, electrical here, and there's a little fuse usually. If it goes wrong, the fuse uh, stops the heater, so it won't have a fire. And then a little key here to turn it on and off. So water basically gets heated around 90 Fahrenheit, 95, no, more than that. I'm sorry, 90 degrees C. Then it goes up, basically a little tube goes up and it drips on top of the coffee here. And then coffee here has many things that it doesn't dissolve in water, right? So the material that dissolves in water or hot water here, including the caffeine, different flavors, and the smell, goes to your pot, and that's what you drink from. Now, obviously, there are other units and machines that we use hot water or steam, and we won't go through that. So this is the just a typical coffee machine that we have. And then the textbook actually asking us a question about this. I'll turn the page over. So it's asking us problem number 1.5. What is this process? Is it asking us, is it a distillation, filtration, or chromatography? If you look at the solution book, it says filtration. It depends. Now, it might be filtering the ground and something that is not soluble, but to me, it's really extraction. So extraction process is a process that we take a portion of molecules or package or something away from it and we use it. So in this case, we take the coffee ground and extract caffeine and other tasty material, smells good, away from the uh, fibers and we drink it. So to me, we call this an extraction, not filtration. Then the textbook has a couple of examples that I like to use to just part of the exercise. So this is number part D. So again, We pretend we are working in a coffee shop. We know if you take 1 pound of coffee, 1 pound of coffee, it makes 50 cups. It makes 50 cups. Now the boss comes and says, "Oh, Perus, we're going to have to need a lot more coffee to make. We have to make 200 cups. We're going to get a lot of customers today. So the question is, how many pounds do I need to go pick up from the grocery store or look at the storage and pick it up?" So these are what we call factors. Now, there are different ways to do the factors. I like the ratio ones that I talked about it before, or we can use what the textbook has. Let's do the textbook. So we know that if I have 1 pound of coffee, that makes 50 cups, right? So we need to make 200 cups, right? So the factor that we use, the cups has to be at the bottom. The cups have to be at the bottom. So that means I put the 50 number 50 here. So remember the factors. When we have a cups here and this cups here, they cancel. So the key is make sure that if you put in the factor here, these two cancel. Now, 50 cups is the same as 1 pound here. So I can put 1 pound here. Now, I know 1 pound is, I'm sorry, 1 kilogram is 2.205. So now I have to put pound here and kilogram here. So we said what did I say? Oh, 1 kilogram, right? So if I have 1 kilogram here, then 1 kilogram, the textbook used 2.205 pounds. So again, the pounds and the pound cancel. So if I divide 200 by 50, 50 cups, times 1 divided by 2.205. So the only thing left is the kilogram, right? Cups and cups cancel, pounds and pound cancel. So now this would be 1.81 kilogram. When we talk about the rounding numbers, which is a significant figure, so this roughly is about 2 kilograms. So if I go buy 2 kilograms of coffee based on the boss, and he said we're going to make 200 cups, that's enough to make 200 cups of coffee for us. Again, factors. So we're going to do a lot of factors during this class, and we need to be prepared for it. Okay, so in problem chapter 3, 53, we have a new thing about coffee, and we're going to do this a lot. Typically, when we have a molecule, we can actually burn it and measure how much carbon we have, how much hydrogen, nitrogen, sulfur, oxygen, and we're using that data to find out what is the compound is made of. The number of carbons, number of hydrogen, number of nitrogen. We cannot tell the structure from this data, but we can tell how many carbons we have. Now let's take a look at it. We know that nitrogen. We know nitrogen is what those textbook has 14.01 gram per mole. So we look at the carbon, nitrogen, oxygen. So let's look at the okay. So let's go back to this coffee problem. Now we know the problem says we have 49.5% carbon. So we know if you look at the periodic table, carbon has a atomic mass of 12.01. So if I take this percent and I assume you have 100 grams of this caffeine made it into CO2 and etc. that we measured percent carbon from it. So out of 100 grams, we can say if we have 49.5 grams of carbon. So if I use that 49.5 gram, not percent, gram, times 1 mole divided by 12.01 gram per mole for the uh, carbon. So that's about 4.12 mole of the carbon. So let's do that for the remaining. So this is the carbon. Then hydrogen, for the hydrogen, we have 5.1%, 5.15 times 1 mole divided by 1.00, what is it, 1008, yes, 1008 on periodic table, 8 meals. So that's become 5.11. Then we have nitrogen. So the nitrogen is 28.9 times 1 mole of nitrogen. And then the atomic weight for nitrogen is 14.01. So this will become 2.06. You still have the oxygen. So I'll put the oxygen here, 16.5 times gram of oxygen, 1 mole of oxygen, 16.00. Sorry, 16.00. That becomes 1.03. So the trick of the trait, as we learn, is that we divide all these number of moles by the smallest number. The smallest number is 1.03. So we divide 1.03 for the oxygen. 1.03, 1.03, 1.03. Of course, the 1.03 would be 1. This roughly is 4. This is 5, 2. So if I look at the as it is, this would be C4, I'm sorry, C4H5N2. Oh, right. Typically for the chemical structure, organic chemical structure, we put the carbon first, hydrogen, then we do alphabetical order. So N comes before O. Now, if you add all these numbers for carbon, hydrogen, nitrogen, oxygen, we get 97. But we were told molecular weight for the caffeine is 195. So the ratio between 195 to 97 is about 2. So real caffeine basically has uh, double these numbers. So we have 8 carbon, 10 hydrogen, 4 nitrogen, and 2 oxygen. Now we know the empirical formula for this caffeine, but we cannot do this structure. We cannot say C8H10N4O2 what the chemical structure is. We have going to learn other methods and technique to learn what the structure is. Here we only know the empirical formula. We know that caffeine is made of 8 hydrogen, 10 hydrogen, I'm sorry, 8 carbon, 10 hydrogen, 4 oxygen, making all mistake. Start over again. 8 carbon, 10 hydrogen, 4 nitrogen, and 2 oxygen. Okay, so the last problem that I found using our textbook was this pH. So it's asking, is coffee more acidic or less acidic than lemon juice? Then we have the table. It's hard to read it here, but I wrote it down here. So lemon juice says 1.1 times 10 to negative 2 as hydronium ion concentration. So this is something we're going to learn. So we know now the concentration of H plus, concentration of H plus for lemon juice is 1 point times 10 to negative 2 mole, we call it, per liter. Now, where does the 2 come from? So the 2 comes from if you take negative log of hydronium ion, so that's what we call a pH. So negative log of 1 times negative 2 is 2. So that's the pH. Now, first of all, why are we doing that? Now, 1 times 10 power negative 2 is a very small number. So we have trouble actually have a concept of that. For the coffee is 1 times 10 negative 5. So which one is bigger? Which one is a smaller? So taking a negative log and making a number from it, 2 and a 5, it actually makes it a lot easier to grasp which one is bigger, which one is uh, smaller. So smaller pH, a smaller pH is more acidic. So if I look at 2 and 5, 2 is a smaller number. So that means lemon juice is more acidic, has a smaller number than coffee, which is 5. So again, these are reminding us for this class, we need to go back and look at the hydronium concentration, mole per liter, and negative log. What is the negative log and how to calculate that? So I might put something up there later on for negative log and how to calculate that. So far, we talked a lot about the coffee, and so this ends the discussion about coffee. If you have questions, please call me, text me, and we can talk about that. Take care.